Back Science Education Consultants, a group of experienced young, strong teachers that are here to make you learn day by day from wherever you are. Regardless of whatever you are going through, we are saying learning must continue taking place. And today we have come to study about physical equilibria, specifically about Rhodes' law. Rhodes was a scientist, and he's the one who studied vapor pressures of different solvents, especially the ones which are volatile. And today we are going to use his law or his finding to do some calculation. I want to assume two examples of liquids. I want to consider hexane. This is a colorless liquid, light colorless liquid, and heptane. Maybe let me make it be hex, and I consider heptane, which I can call HEP. These are two liquids which are almost the same. Hexane is C6H14, heptane is C7H16. They are very close. They are alkanes. They have almost the same bonding in them, but they are very volatile. Very volatile in a way that if I have here hexane, it will keep fuming. It keeps on fuming. What causes fuming? It's just the ability of the molecules in liquid form to overcome the forces that make them liquid, and they escape into vapor phase. Meaning, when they reach vapor phase, there are conditions that can help them to turn back into a liquid. If those conditions are there, it means that some molecules can still turn from vapor phase to the liquid. So we shall have vaporization, an indicator that we must have some vapor of hexane. So if this is the liquid, then we must have some vapor of hexane. This vapor of hexane will exert a pressure on the surface of hexane, which I can represent as P. Let me use P, a vapor pressure called maybe PHEX. Let me even put there a note. This is pure hexane liquid, and it vaporizes. It has vapor which is in contact with hexane liquid, and at equilibrium we have this as P0H2X. P0HEX is called vapor pressure of pure hexane. Likewise, since heptane is also volatile, we can have P0 of HEP as vapor pressure of pure heptane. Meaning that you have these two liquids in the two different beakers. For example, each one of them is fuming. I want to ask you a question. If you mix these two liquids together, can they fume the way they fume when they are pure? If I get hexane, I mix it with heptane, can the solution formed allow vaporization of hexane and heptane the way they were when they were pure? The answer can be yes, the answer can be no, depending on how they interact. Rhodes' law studied this science and came up with a law which helps us estimate the amount of the substance that can vaporize in solution form. So, I'm going to assume that I have mixed both of them. So that this is now a mixture of hexane and heptane. A mixture of hexane and heptane. An indicator that since they are volatile, they will fume. Definitely they will fume. We don't know that they will fume the way they fume when they are pure, but the fact is they will fume. Meaning that the total pressure on the surface of this liquid, the total pressure, will be equaling now to the pressure that is as a result of fuming of hexane, but in this solution, which is not necessarily the same as this pressure that we have seen before. And we also have heptane fuming. Each of these ones will contribute to the total pressure. So, the P hex is called the partial vapor pressure. And P hept is the partial vapor pressure also. This is for hexane and this is for heptane. So we are emphasizing that P naught hex is not the same as P hex. Also, P naught hept is not equal to P. Why? When you mix these two liquids, provided they have formed a solution, provided a solution is formed, there must be interaction. There must be attraction of hexane molecules with heptane molecules. Regardless of whether that attraction is high or low, but there must be attraction for the two liquids to form a solution. An indicator that if you had molecules of hexane evaporating freely when they are together, they are the same, they are uniform in the pure hexane. In this case, some of them are attracted, some of them are fixed with heptane molecules. In the same way, heptane molecules, some of them cannot go freely, they are attracted with hexane. At times, you might find it is the opposite. We shall see that when we have seen deviations from Rhodes' law. So, we have to emphasize that the way hexane vaporizes when it is pure is not the same way it can vaporize when it is in solution. So that's why actually we are calling them partial vapor pressures. Where are we going? We have to first define definitions, and I want you to go and look for these definitions. I want you to go and look for these definitions. Define the terms. The first one, vapor pressure. And the second one, partial vapor pressure. Please go and they are very important terms that we must learn their definitions. We must know what they mean and we must continue using them. How did Rhodes exploit this science? he stated his law that the partial vapor pressure of a volatile component in a solution is always the product of its vapor pressure when it is in its purest form and its mole fraction in the solution. In other words, for you to get the amount of the solvent that can vaporize in solution, the partial vapor pressure, for you to know it, you should be able to know how this solvent vaporizes when it is in its purest form, and you must be knowing its percentage composition or its content within the solution. In other words, if X is the mole fraction, then we shall find that the partial vapor pressure P will be equaling to X P naught. Specifically, if I come back here, if I use what we are using to now, I use hexane and heptane, the amount of hexane within the vapor P hex, the vapor pressure of hexane, will always be equaling to the amount of hexane in this solution times its vapor pressure in its purest form. This will help us to determine the content, the composition of our vapor. How important is this? It is very important when you are carrying out separation of substances by distillation. You can easily know when and how to correct some components of the solution that you are interested in. There is a reason why I'm using hexane and heptane. These two liquids, when mixed together in any proportion, they obey Rolle's law. They are among the very few examples of liquids that can obey Rolle's law. In other words, the liquids that can obey Rolle's law are the ones which we call ideal solutions. They are very, very few. Like the word ideal says, something that is ideal almost does not exist practically. So, I want us to have some other examples of ideal solutions, and we calculate something small, and we call it a lesson. Can be summarized as P equaling to X P naught. If I have the way I had my liquids, like I've said, P hex will be X of hexane, the amount of hexane in solution times its mole fraction, and also for heptane it will be the same. But in these two, if at all we consider the solution that we had made, if you have only two solutions two liquids in that solution, it means that when you get the fraction of hexane and you add there the fraction of heptane, you will always get 1. If at all they are in percentage, if you have the percentage of hexane plus the percentage of heptane, they should add up to 100. Meaning that these three equations can be used to calculate anything about our solutions, as we are going to see examples. I want us to write this question and we do it. We apply Rod's law and we do it. A solution containing 80% of x and 20% y forms an ideal solution. This is very important. If the vapor pressure of x and y respectively at the same temperature are 100 atmospheres and 500 atmospheres, calculate the total vapor pressure of the solution. And its percentage composition. Why should this be an ideal solution? We have hinted on it that for Rod's law to be obeyed, the solutions must be ideal. We are going to see how ideal solutions look like later on. A solution is containing x and y. It is containing x and y, meaning that if both x and y can vaporize, because definitely for something to have a vapor pressure of 100 atmospheres and 500 atmospheres, they must be volatile. Then there must be total vapor pressure, which will be equaling to vapor pressure of x plus vapor pressure of y. Remember that the vapor pressure of pure x, the vapor pressure of x at a particular temperature where this experiment was carried out is 100 according to this question, and the vapor pressure of y is 500. What does this one communicate to us? It shows us that x is volatile and y is volatile. But which one is more volatile than the other? Definitely y is more volatile since it has higher vapor pressure. There is more of the vapor on top of the solution of y than the solution of x. Remember that we are looking for total vapor pressure, which we have said is the sum of px and py. Can we maybe start from there? The total pressure is P of x plus P of y, the partial vapor pressures. But the partial vapor pressure of x is its mole fraction in solution and its vapor pressure in its purest form times its partial vapor pressure in its purest form. Meaning that we can have this as the fraction of x. If you have a solution containing 80% x, means that the fraction of x in solution is 80 over 100 times the p times the p naught of x, which is 100, then plus 20 over 100 times 500. And this, from my calculator, you can use yours. I have this as 80 plus 100, which is equal to 180 atmospheres. This is the total vapor pressure. So, the total vapor pressure on top of this solution will be 180. What is its composition? The percentage composition of this vapor pressure. In other words, we want to look for how much of X is in this vapor, how much of Y is in this vapor. For X, let me say percentage of X will be, remember, X contributes 80 in this pressure. So it will be 80 divided by 180. Use your calculator and make sure when you get the answer that looks like mine, you celebrate. This one has no units. Remember, 80 is in atmospheres, and also this is in atmospheres. They cancel. But we are looking for the percentage. We are looking for the percentage, and therefore we must multiply this by 100. So possibly this will be 44%. The percentage of Y will be 100 over 180 times 100. From your calculator, please do it and make sure you get 56%. Remember that since these are two liquids mixed together, you may not even do the second one. After getting 44%, you can get 100 and you subtract. You will still get 56 because the total percentage must be 100. Can we go back to our question? In the solution, we have there 80% of X and 20% of Y in the solution. After mixing them together and they vaporize, the vapor that comes out is not containing 80% of X. It is not containing 20% of Y. Instead, it is containing 44% of X and 56% of Y. In fact, X was 80%, but now it is lower. This one, which was 20, is now 56. This is what it means, that X is more volatile than Y. If you mix them together, Y easily turns into vapor before X. We have a good number of questions, very many of them related for you to practice. We are here at Back Science Education Consultants. Please contact us and we'll keep practicing. We have a good number of them. WhatsApp us, send us an email, dukescireconsult@gmail.com, and go to our YouTube. We shall have those questions posted there. Otherwise, for today, I'm happy to have you as my learner. Be safe and continue learning.